Hello YouTube, this is a third video in a series of videos I'm doing on counting, and in this video we are focusing on, or at least building on, our prior knowledge of permutations, but we're going to focus on a number of distinct permutations, okay? And this is kind of an interesting concept. We say distinct things, or things that can be told, one from the other, okay? So if it's distinct, it's obviously one thing and not another. So for example, let's take a look at what I've written up here. It says up until now, we've been finding permutations of distinct objects, okay? If some of the objects are repeated though, then some of the permutations are not distinguishable. Like I wouldn't be able to tell one from the other unless I'd written it as I've written it here. So for instance, I say the 6 ways to order the letters M-O-M. So like the word mom here. Let's assume that every letter in the word mom has a color, okay? So like O is black, one of the M's is red, another of the M's is green. But you can see that there are actually 6 different ways to list these letters here, where we have like the red M comes first, or the green M comes first in 2 of them, and the black O comes first in 2 of them. But notice this, like if we look at, say, this example here, let's go over to our pen tool, change to like a red. You'll notice that these 2 here, we cannot distinguish one from the other unless we color the letters, and of course we're not coloring the letters most of the time. Also this way, you say this one here is indistinguishable from this one here, these double underlined things, and maybe we'll triple underline these here, triple underline. But we wouldn't be able to distinguish those either unless we had colored the letters. So when we talk about the number of distinct permutations or distinguishable permutations without coloring things, we have to discount the fact that some of these actually repeat, okay? And so since we had 2 M's, we'd say, well, then I'd say that there are only 3 distinguishable permutations of this, and that would be M, M, O, M, O, M, and O, M, M, because you can see as I write it in like this pink color here, it wouldn't matter if I switch these 2 M's around. It'd still look like OMM. So it says if we don't put letters, in color, then only 3 of these arrangements are distinguishable. What I want to point out is this. We say in this case the number of permutations is 3 factorial, but divided by 2 factorial. And again, recall that 3 factorial over 2 factorial, this just means 3 times 2 times 1 all over 2 times 1. And on the bottom here, this 2 times 1 cancels out with the 2 times 1 on top. We just get left with 3 over 1, or just 3. And this is very, very important. Most of the time we say, well, how many distinct permutations are there of the letters M, O, and M? And typically we say, well, the first letter, we say have to choose an M or an O, or the third M, we'd say there'd be 3 letters to choose from here, 2 letters to choose from then remaining in the second spot, and only 1 to choose from the last one. But that does not work here because repeating letters. So here's what we're going to do. We're going to define the number of permutations with repetition involved to present us with distinguishable permutations or ordering. So we say the number of distinguishable, looking down here, distinguishable, can tell the difference between them. Permutations of n objects, where one object is repeated q1 times and another object is repeated q2 times, and so on and so forth, is this. So we say, still, looking at this formula, n factorial is on top, total number of factorial on top. But we say over the number of times, say, one object occurs factorial, which is q1 factorial. The number of times another object occurs is q2 factorial, and then all the way up to, let's say, some qk. So looking at the example that we just did, we say number of distinguishable factorial, like objects or permutations rather. We could have just put it this way. We say, well, there were 3 objects we were choosing from, so that's our n. So we'd say 3 factorial. Now, this is over the factorial of how many times each individual thing occurs. So we say like the letter M. The letter M occurred twice. It was repeated twice. So we'd say, well, 2 factorial then goes on the bottom times. Now we say what other letters occurred? Well, the letter O occurred. How many times did the letter O occur? Letter O occurred once. So we say 1 factorial. But I thought you said over here that it was 3 factorial over 2 factorial. Well, here's the deal. This 1 factorial, basically anything that doesn't repeat, you could put in a 1 factorial down here because we say, well, O occurred once, so 1 factorial. We could put in a factorial in the basement for every single letter that occurs. But if the letter only occurs once, that is, it doesn't repeat, then we're going to be putting in a 1 factorial down here for it anyways. And what do we know about 1 factorial? 1 factorial just equals 1. What do you know about anything times 1? It is itself. So really, using this definition that we've got here, we basically say the total number of objects that are present, say letters in this case, factorial, over however many times given objects repeat, like 2 factorial. Okay, so because m occurred twice, you know. So let's take a look at these 3 examples here. We're talking about distinguishable permutations of, say, a word, you know, letters in a word. And so, like, these are common examples you might see, but we say Ohio. Okay, so let's take a look at Ohio first. We say, how many different ways could you rearrange the letters in the word Ohio, but, like, you know, have them be distinguishable from one another? You know, not like have one O is red and the other one is green, and, you know, that makes a difference. But we say, okay, so in this case, we say, all right, well, we got 4 letters. So let's start with it. We say 4 factorial is our n factorial. Now, we could do this. We could write this as, well, O occurred twice. So we say 2 factorial times, now H occurred once, 1 factorial for our H, times I occurred once. So we say 1 factorial. I don't want to do this, though, and the reason why is because we don't have to care about these 1 factorials. The only letters we cared about here were these O's right here, because these O's repeated twice. So really the quick way to do this is to say, well, there are 4 letters. O repeats twice, so we say 2 factorial. Now, you know, simplifying this, we get 4 factorial is, of course, 4 times 3 times 2 times 1 over 2 factorial, which is 2 times 1. And our 2 and 1 here, cancel out 2 and 1 here. We get 4 times 3. This means that there are 12 distinguishable ways you could rearrange the letters, the 4 letters in Ohio. So now let's take a look at the word banana. Okay, so banana. We say, all right, how many letters are in banana? We say 1, 2, 3, 4, 5, 6 letters. So we're rearranging 6 things, 6 factorial. We say, how many repeat? Now, B happens once. I don't care about the B, but A happens 3 times. So we say 3 factorial for our A times, now I notice N happens twice. So 2 factorial. And I want you to notice one more thing. If we were to put in the 1 factorial for your B, all these factorials on the bottom, 3 plus 2 plus 1, add up to the 6 that you've got on top here. And that should happen, okay? But we said writing this out. This is important you write this out this time. And the reason why is because you get RL, you know, 6 times 5 times 4, holy shnikes, times 3 times 2 times 1, all over 3 factorial. So 3 factorial is 3 times 2 times 1. And that's times 2 factorial, which is 2 times 1. So now discounting all these 1s, we don't really care about those. We say, well, maybe this 3 and this 2 cancel out with this 3 and this 2 here, but this leaves this 2 down here. Now, if you're talking about the number of ways to rearrange letters in something, you're not going to come up with a fraction, which means whenever you do these permutations, you should always end up with a whole number, meaning everything on the bottom cancels out with something on the top. So this 2 down here, we could say cancels out with this 4 on top or with the 6 on top. I like to knock down big integers, so we say, well, maybe this 2 down here becomes a 1, and 2 goes into 6 3 times. So now on the top we have 3 times 5 times 4, or 3 times 5 is 15, 15 times 4, 4 15s is 60. So there are 60 distinguishable ways to permute or order the letters of banana. So now Mississippi, oh my goodness, I remember doing this one when I was in high school. So first of all, how many letters are in Mississippi? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we say 11 factorial. Make this a big fat factorial here. All over. Now we say, okay, so M happens once. We don't care about that. We want repeaters. We say, how many times does I happen? So we say I. I repeats 4 times. So we say 4 factorial. Times now S occurred 4 times. So 4 factorial. So on the bottom we have a total of 8. Okay, and the M made 9, so we have 3 more left. So we say, all right, so S and I accounted for, M accounted for, P occurred twice. So we say 2 factorial. So now writing this out, it's not so bad. We say 11 times 10 times 9, honestly, this is the worst part, times 8 times 7 times 6 times 5 times 4 times 3 times 2, and just for you YouTubers, I'll put the 1 there, even though usually I don't write it. And now this is all over. Okay, let's talk about our first 4 factorial. We got 4 times 3 times 2 times 1 times another 4 factorials, 4, 3, 2, 1, times a 2 factorial, 2 times 1. Let's start canceling things out. All of these 1s in products with things, those are multiplicative identities anyway, so they cancel out. And we say this 4, 3, 2 here cancels out with, say, this 4, 3, 2 up top. So let's reduce the things we have left, starting with, say, this 2 on the end. Now this 2 on the end, I like to pass it again into larger even numbers. So we say the 2 would cancel out with, say, this 10. This 10 would now become a 5. How about this other 2 here? We say 2 would cancel out with another of these even integers. Let's go with this big 8. We say now 8 would become a 4. I also notice that this 4 down here cancels out with this 4 here, knocking it out completely. We say 3. Now 3 would pass into, say, our 9 or the 6. Let's pass our 3 into our 9. We say 3 goes into 9 3 times. So I like to put a box around the remaining things here so that I know what I'm supposed to be multiplying. But those 3 here. Okay. So 11 times 5 times 3, so that would be 55 times 3 times 7 times 6, which is 42 times 5. Or in other words, we'd have 55 times 42 times 3 times 5, which is 15. So we get this. We get 55 times 42 times 15. So 55 times 42 times 15. We say 34650. There are 34,650 ways to distinguishably rearrange letters in Mississippi. Now I do want to point one more thing out before we go. Don't depart, just to show you this. We say 11 factorial over 4 factorial, 4 factorial, 2 factorial. A couple things. First of all, 4 factorial times 4 factorial times 2 factorial. This is like a huge sin. Don't do this. We say 4 times 4 is 16 times 2 is 32. 32 factorial. This is so not true. Don't do this to yourself. It's embarrassing. You'll be sitting by yourself at lunch if people see you do this, okay? And the other thing is this. We can just put this in the calculator, kind of like verbatim, word for word, even though these aren't words, they're numerals. But we say, all right, so 11 factorial. Now we were dividing this by, now I want to put this all in parentheses, but we say 4 factorial times 4 factorial times 2 factorial, end parenthesis. But you'll notice here that the calculator is going to spit out the same result. But that would have saved you a lot of time. But reducing by hand is a good thing to know how to do. So, you know, just a really kind of brief video on how to find distinguishable orderings or permutations.